Welcome to Tech with Kaushik. This is set 13 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 13. Next, question number 222. This one focuses on automated EC2 isolation. A Security Operations Center, SOC, oversees a multi-account AWS organization's environment. When an Amazon EC2 instance is suspected of compromise, analysts apply a tag with key status and value isolated. The SOC wants the tag to trigger rapid, reversible network containment of only that instance while preserving it for investigation. A DevOps engineer must deploy the event-driven containment mechanism consistently across all workload accounts. Which combination of steps should the engineer take to implement this solution? Choose 2. Choose every option that satisfies the requirement. Option A. Create an Amazon Event Bridge rule that detects the relevant EC2 tagging API event and starts the AWS Systems Manager Automation Runbook AWS support. Contain EC2 instance in contain mode for the tagged instance, using a dedicated automation role with least privilege permissions. Option B. Use AWS Cloud Formation stack sets from the management or delegated administrator account to deploy the Event Bridge rule, automation role, and supporting containment configuration uniformly across the required organization accounts. Option C. Create an AWS Cloud Formation template that deploys a restrictive network ACL. Include an AWS Lambda function that associates this network ACL with the instance's subnet. Use an Amazon Event Bridge rule to trigger the Lambda function when the specific tag is applied. Option D. Create a service control policy, SCP, with a deny statement for EC2 * actions conditionally applied when AWS request tag /status equals isolated. Attach this SCP to the root of the organization. E. Use AWS Systems Manager Quick Setup to automatically distribute the event-driven Lambda automation architecture to all organizational units. The correct answers are Option A. Create an Amazon Event Bridge rule that detects the relevant EC2 tagging API event and starts the AWS Systems Manager Automation Runbook AWS support. Contain EC2 instance in contain mode for the tagged instance, using a dedicated automation role with least privilege permissions. And Option B. Use AWS Cloud Formation stack sets from the management or delegated administrator account to deploy the Event Bridge rule, automation role, and supporting containment configuration uniformly across the required organization accounts. This is the best choice because AWS provides the AWS support. Contain EC2 Instance Systems Manager Automation Runbook specifically for EC2 network containment. It backs up the current security group configuration and replaces it with a restrictive containment security group with restore support. Event Bridge can start the automation in response to the tagging event, and Cloud Formation stack sets is a native way to deploy the event rule and required IAM/supporting resources across many organization accounts. Let's quickly check the incorrect choices. C. A network ACL is associated with a subnet, so replacing the subnet ACL would affect other resources in that subnet rather than containing only the tagged instance. D. An SCP controls authorization to AWS AP it does not isolate the instance's data plane network traffic. E. Systems Manager Quick Setup is intended for supported predefined Systems Manager configurations. Stack sets is the direct organization scale mechanism for distributing this custom Event Bridge/IAM containment configuration. Here's a useful exam tip. For reversible EC2 incident containment, prefer Systems Manager automation such as AWS support. Contain EC2 instance. Use stack sets to deploy the trigger and permissions at organization scale. Question number 223. Scenario. A development team hosts their application source code in an AWS code commit repository. They use AWS Code Pipeline to orchestrate their CI/CD workflow. When a developer merges a pull request into the main branch, an AWS code build project runs automated unit tests. The release manager has requested an update to the process. If the unit tests pass successfully, the code build project must automatically apply a git tag to the specific commit that triggered the build and push the tag back to the code commit repository. How must the DevOps engineer configure the code build project to achieve this? Choices. Option A. Configure the code commit source action in code pipeline to use the full clone output format, so the downstream code build action receives a Git URL reference and Git metadata. Grant the code build service role the required code commit Git permissions, then use native Git commands after successful tests to create and push the tag. Option B. Allow code pipeline to pass the source code as a zip artifact to code build. Execute the tests, and if successful, use the AWS code commit tag resource AWS CLI command to tag the commit. Option C. Allow code pipeline to pass the source code as a zip artifact to code build. Execute the tests, and if successful, initialize a new Git repository locally, commit the files, and use native Git commands to push the tag. Option D. Configure the code build project to clone the repository using native Git. Execute the tests, and if successful, use the AWS code commit create commit AWS CLI command to generate a new tag on the repository. The best choice is option A. Configure the code commit source action in code pipeline to use the full clone output format, so the downstream code build action receives a Git URL reference and Git metadata. Grant the code build service role the required code commit Git permissions, then use native Git commands after successful tests to create and push the tag. The default code pipeline code commit source output is a zip artifact and does not provide the .git metadata needed for normal Git history operations. The code commit source action supports a full clone output that downstream code build can use to clone the repository with Git metadata. With the required Git permissions, the build can tag the triggering commit and push the Git tag after the tests succeed. B. Code commit tag resource applies AWS resource tags to the repository resource. It does not create a Git tag on a commit. C. Creating a new unrelated local Git repository does not preserve the triggering repository's commit history and is not the supported code pipeline full clone integration. D. Code commit create commit creates a source commit. It is not an API for creating Git tags. The main takeaway is when code build needs Git history or Git commands in a code pipeline workflow, configure the source action for full clone rather than the default zip artifact. Next up is question number 224. A company runs microservices on an Amazon Elastic Container Service, Amazon ECS, cluster backed by an auto-scaling group of Amazon EC2 instances. Occasionally, tasks exit unexpectedly during scale-out events or due to memory constraints. A DevOps engineer needs to capture the exit codes and stop reasons for every task that transitions to a stopped state. The solution must provide a centralized way to query and review these error details with minimal operational overhead. Which implementation satisfies these requirements? Choice A. Enable ECS container insights and configure the tasks to output logs in embedded metric format, EMF. Monitor the task count CloudWatch metric for sudden drops. Choice B. Implement an Amazon event bridge rule that matches ECS task state change events. Route these events to an Amazon CloudWatch logs log group and use CloudWatch logs insights to analyze the stopped tasks. Choice C. Install the CloudWatch agent on the underlying EC2 instances. Create a CloudWatch contributor insights rule based on the instance-level system logs to identify task termination events. Choice D. Configure an EC2 auto-scaling lifecycle hook targeting the EC2_instance_ terminating event. Trigger a Lambda function to write the instance state to an Amazon S3 bucket and query the data with Amazon Athena. Go with option B. Implement an Amazon event bridge rule that matches ECS task state change events. Route these events to an Amazon CloudWatch logs log group and use CloudWatch logs insights to analyze the stopped tasks. Let's look at the reasoning. Amazon ECS natively emits ECS task state change events to Amazon Event Bridge whenever a task transitions between states, for example, running to stopped. These events contain detailed metadata, including exit codes and stop reasons. Routing these events to a CloudWatch logs log group provides a durable, centralized repository that can be easily queried and filtered using CloudWatch logs insights with minimal operational overhead. Now let's rule out the other options. A. Embedded metric format, EMF, is used to generate custom CloudWatch metrics from application logs. It does not automatically capture ECS platform-level state transitions or task exit codes. C. EC2 system logs and CloudWatch contributor insights do not provide native, structured visibility into ECS task definitions, containers, or the specific reasons the ECS control plane terminated a task. D. EC2 auto-scaling lifecycle hooks trigger when the underlying EC2 instance scales in or out. They do not trigger when an individual ECS task stops due to application failure or memory constraints while the EC2 host remains healthy. Exam tip: to monitor, audit, or respond to state changes in ECS tasks, like unexpected terminations, always rely on the ECS task state change events emitted natively to Amazon EventBridge. Question number 225. Let's go. Next, let's move into code deploy blue/green hooks. An engineering team uses AWS Code Deploy to orchestrate updates for an application hosted on an Amazon EC2 auto-scaling group behind an application load balancer. The deployment process requires the following logic. A fresh set of replacement instances must be provisioned automatically without manual intervention. Traffic must be routed to 50% of the new instances at a time. The deployment is considered successful if at least half of the instances are healthy. Crucially, a custom script must run to clean up temporary installation files on the new instances just before live traffic is routed to them. If successful, the original instances must be terminated immediately to optimize costs. Which code deploy configuration fulfills these requirements? Options. Option A. Implement a blue/green deployment tied to the application load balancer target group. Select code deploy default half at a time as the deployment configuration. Configure code deploy to terminate the original instances and execute the cleanup script using the before allow traffic lifecycle hook in the appspec.yml. Option B. Implement an in-place deployment. Select code deploy default half at a time as the deployment configuration. Configure the auto-scaling group integration to replace instances and execute the cleanup script using the allow traffic lifecycle hook in the appspec.yml. Option C. Implement a blue/green deployment tied to the application load balancer target group. Define a custom deployment configuration requiring a minimum of 50% healthy hosts. Configure code deploy to terminate the original instances and execute the cleanup script using the before block traffic lifecycle hook in the appspec.yml. Option D. Implement an in-place deployment. Select code deploy default all at once as the deployment configuration. Configure the auto-scaling group integration and execute the cleanup script using the block traffic lifecycle hook in the appspec.yml. The right response is Option A. Implement a blue/green deployment tied to the application load balancer target group. Select code deploy default half at a time as the deployment configuration. Configure code deploy to terminate the original instances and execute the cleanup script using the before allow traffic lifecycle hook in the appspec.yml. Here's why. A blue/green deployment automatically provisions the required fresh replacement instances without manual intervention. The code deploy default half at a time deployment configuration ensures the application is installed and validated on half the instances at a time. The before allow traffic lifecycle hook specifically targets the new replacement instances just before the load balancer begins routing live traffic to them, making it the correct place for cleanup tasks. Code deploy natively supports immediate termination of original instances upon success. The other choices do not work because B. An in-place deployment installs the update over the existing instances. It does not automatically launch a new fleet of instances as required by the scenario. Furthermore, allow traffic happens after traffic is permitted, which is too late for pre-traffic cleanup. C. The before block traffic hook runs on the original instances before they are deregistered from the load balancer, not on the replacement instances. Running the cleanup script here would alter the old environment, not the new one. D. An in-place deployment does not fulfill the blue/green requirement. Additionally, block traffic runs on the original instances and all at once violates the requirement to route traffic to half the instances at a time. In AWS Code Deploy blue/green deployments for EC2, hooks like before block traffic run on the original environment, while before allow traffic runs on the replacement environment before it serves user traffic. Now for question number 226. Consider this situation. A software organization is migrating to a centralized multi-account AWS architecture. They have deployed AWS Control Tower in their AWS Organizations Management account to serve as the landing zone and enforce preventive guardrails. The architecture team must define a standardized baseline infrastructure, including customized VPCs, IAM roles, and security logging, that must be automatically present in every new workload account immediately upon creation. Which approach guarantees this baseline is applied to new accounts with the least operational overhead? Here are the options. Option A. Use AWS organizations to provision new accounts. Configure an Amazon Event Bridge rule that detects the Create Account API call and triggers an AWS Lambda function to assume an administration role and deploy the baseline. Option B. Define the baseline infrastructure as an AWS Control Tower Account Factory Customization (AFC) blueprint using AWS Service Catalog. Provision all new workload environments through the account factory using this blueprint. Option C. Provision new accounts using the AWS Control Tower Account Factory. Manually log into each newly provisioned account as the administrator and deploy the baseline via AWS CloudFormation. Option D. Provision new accounts via AWS organizations. Use AWS CloudFormation stack sets from the management account to target the entire organization and apply the baseline infrastructure globally. The answer here is option B. Define the baseline infrastructure as an AWS Control Tower Account Factory Customization (AFC) blueprint using AWS Service Catalog. Provision all new workload environments through the account factory using this blueprint. This works because AWS Control Tower Account Factory Customization (AFC) is explicitly designed to automatically apply customized, standardized infrastructure baselines to new accounts during the provisioning process. By defining the baseline in an AWS Service Catalog blueprint and attaching it to the account factory, Control Tower handles the seamless rollout of these resources with zero manual post-provisioning steps and minimal operational overhead. Here's why the alternatives are not suitable. A. Building a custom event bridge and Lambda architecture to detect create account events and deploy baselines is essentially reinventing Control Tower's native capabilities, introducing significant operational overhead and maintenance burden. C. Manually logging into accounts to run CloudFormation templates is highly error-prone, unscalable, and strictly violates the requirement for the least operational overhead. D. While CloudFormation stack sets can deploy across an organization, managing account baseline provisioning via standalone organizations and stack sets bypasses the integrated, managed governance benefits of Control Tower Account Factory, requiring more manual alignment. A helpful shortcut is this. When using AWS Control Tower, the most native and efficient way to deploy a mandatory infrastructure baseline to all newly created accounts is Account Factory Customization, AFC. Question number 227. Scenario. A security compliance team manages auditing for an AWS organization's environment. To adhere to strict internal policies, the team must be immediately alerted via their third-party monitoring system, integrated via Amazon SNS, whenever an AWS account root user logs into the AWS Management Console anywhere in the organization. Additionally, the security team requires an on-demand dashboard to visualize and review the historical log activity generated by these root user logins. Which combination of configurations meets these requirements? Choose 3. Select all answers that apply. Options. Option A. Implement an AWS Cloud Trail organization trail that is configured to deliver all management events to a centralized Amazon Cloud Watch Logs log group. Option B. Create an Amazon Cloud Watch Logs metric filter on the centralized log group that specifically matches console login events where the user identity is root. Use this filter to trigger a CloudWatch alarm that publishes to the target SNS topic. Option C. Build an Amazon CloudWatch dashboard that utilizes a CloudWatch Logs Insights query to filter, format, and display the root user login events from the centralized log group. Option D. Create an Amazon CloudWatch Logs subscription filter on the centralized log group to match root user login events and forward them directly to the target SNS topic. E. Enable an AWS config multi-account aggregator in the management account and configure it to forward compliance state changes to Amazon CloudWatch Logs. F. Build an Amazon QuickSight dashboard and connect it directly to the CloudWatch Logs metric filter to visualize real-time root user logins. You should choose option A. Implement an AWS Cloud Trail organization trail that is configured to deliver all management events to a centralized Amazon Cloud Watchlogs log group. Option B. Create an Amazon Cloud Watchlogs metric filter on the centralized log group that specifically matches console login events where the user identity is root. Use this filter to trigger a CloudWatch alarm that publishes to the target SNS topic. And Option C. Build an Amazon CloudWatch dashboard that utilizes a CloudWatch Logs Insights query to filter, format, and display the root user login events from the centralized log group. The main reason is to monitor events globally across an organization. An AWS Cloud Trail organization trail must route management events to a central CloudWatch Logs log group. From there, a CloudWatch metric filter can continuously parse the logs for the console login and root identity pattern. When a match occurs, a CloudWatch alarm triggers and pushes the alert to SNS. Finally, CloudWatch Logs Insights provides the ad hoc query capabilities needed to visualize these historical events natively on a CloudWatch dashboard. The remaining options can be eliminated because CloudWatch Logs subscription filters support destinations such as Lambda, Kinesis data streams, Firehose, and OpenSearch service. Amazon SNS is not a direct subscription filter destination. A metric filter plus CloudWatch alarm can publish to SNS natively. AWS config tracks changes to resource configurations, for example, security groups, EC2 instances. It is not designed to capture transient API calls or authentication events like a user logging into the console. Amazon QuickSight is a BI tool primarily used for data warehousing and business analytics. While it can connect to diverse sources, native CloudWatch dashboards utilizing Logs Insights are the standard, lowest overhead tool for operational log visualization. Keep this point in mind for the exam. For organization-wide root console login alerting, centralize Cloud Trail management events, create a CloudWatch Logs metric filter, and alarm to SNS, and use Logs Insights/dashboard widgets for historical review. Next, question number 228. This question takes us into Identity Center SAML and SCP. A corporate IT department relies on a centralized multi-account environment managed through AWS organizations. A recent security audit mandated that all human access to the AWS Management Console must authenticate strictly through the company's existing on-premises SAML 2.0 identity provider, IDP. To prevent shadow IT and bypass controls, a DevOps engineer must enforce this directive globally and ensure no user can bypass the IDP by creating or using direct IAM user passwords. Which combination of steps should the engineer implement to enforce these requirements? Choose 2. Identify all valid responses. Choices. Option A. Use organization-wide automation to delete any existing IAM user login profiles and member accounts. Then attach an AWS organization's SCP at the root that explicitly denies IAM. Create login profile and IAM. Update login profile so new or changed IAM user passwords cannot be established. Option B. Configure AWS IAM Identity Center, AWS Single Sign-On, in the management account, establishing an identity federation trust with the corporate SAML 2.0 IDP. Option C. Deploy an IAM permissions boundary via AWS Cloud Formation Stack sets to all accounts that explicitly denies password logins for IAM users. Option D. Enable Amazon Guard duty across the organization using delegated administration and activate the rule that strictly denies IAM user console logins. Option E. Centralize IAM user creation by creating IAM groups in the management account and deploying them to member accounts via cross-account trust policies. The answers that work here are Option A. Use organization-wide automation to delete any existing IAM user login profiles and member accounts. Then attach an AWS organization's SCP at the root that explicitly denies IAM. Create login profile and IAM. Update login profile so new or changed IAM user passwords cannot be established. And Option B. Configure AWS IAM Identity Center, AWS Single Sign-On, in the management account, establishing an identity federation trust with the corporate SAML 2.0 IDP. This is the best choice because IAM Identity Center can federate workforce authentication to the corporate SAML 2.0 IDP. To prevent password-based IAM user console access from bypassing that path, existing IAM login profiles must first be removed and an organization-wide SCP must prevent member account administrators from creating or updating login profiles afterward. Let's quickly check the incorrect choices. C. A permissions boundary only limits identities to which the boundary is attached. A member account administrator could create an IAM user without that boundary unless an organization-level control prevents it. D. Guard duty detects threats. It does not enforce IAM console authentication or block creation of IAM login profiles. E. IAM groups in the management account do not provide organization-wide SAML Workforce Federation and do not eliminate local IAM user passwords. Here's a useful exam tip. Federate workforce access with IAM Identity Center. Remove existing IAM user login profiles, and use an SCP to prevent member accounts from recreating password-based console access. Question number 229. Let's go. Scenario. A cloud engineer is deploying a stateful microservice to an Amazon EKS cluster whose worker nodes are Amazon EC2 instances spread across multiple availability zones. The application uses Amazon EFS through the EFS CSI driver and a storage class that dynamically provisions EFS access points. Pods remain in container creating. Investigation shows that the EFS file system has no usable mount target in one worker node availability zone. Its mount target security group does not allow NFS from the node security group, and the CSI controller has not been given AWS API permissions. Which actions must the engineer take to resolve this mounting failure? Choose 3. More than one answer may be correct. Option A. Attach a resource-based policy to the EFS file system, granting the EKS cluster's OIDC provider access to read and write data. Option B. Create an EFS mount target in each availability zone used by the EKS worker nodes, in an appropriate subnet for that availability zone. Option C. Add an inbound rule to the security group associated with the EFS file system to allow NFS traffic, port 2049, originating from the EKS worker node security group. Option D. Configure an IAM role for the EFS CSI driver controller by using IRSA or an equivalent supported EKS pod identity mechanism, and attach the required Amazon EFS SysI driver policy permissions. E. Configure an AWS data sync task to facilitate continuous synchronization between the EFS file system and the local storage of the EKS nodes. F. Modify the Kubernetes deployment manifest to disable in-transit encryption for the persistent volume claim. The required selections are Option B. Create an EFS mount target in each availability zone used by the EKS worker nodes, in an appropriate subnet for that availability zone. Option C. Add an inbound rule to the security group associated with the EFS file system to allow NFS traffic, port 2049, originating from the EKS worker node security group. And Option D. Configure an IAM role for the EFS CSI driver controller by using IRSA or an equivalent supported EKS pod identity mechanism, and attach the required Amazon EFS CSI driver policy permissions. EFS clients need network reachability to an EFS mount target, and a multi-availability zone EKS deployment should have a mount target in each availability zone used by the nodes. The mount target security group must allow inbound NFS on TCP 2049 from the worker nodes. For dynamic provisioning, the EFS CSI controller also needs IAM permissions to call EFS APIs. IRSA remains a supported way to provide those permissions. A. The EKS OIDC provider is used to establish pod IAM identity. It is not directly granted file system data access through an EFS resource policy in this manner. E. Data sync moves or synchronizes data between storage systems. It does not provide Kubernetes persistent volume mounting. F. Disabling in-transit encryption is not required to mount EFS and would weaken the security posture. The main takeaway is troubleshoot EFS CSI storage in 3 layers. Mount targets by availability zone, security group NFS access on TCP 2049, and IAM permissions for the CSI controller when it provisions access points. Question number 230. The focus now shifts to roles anywhere and EFS utils. A manufacturing company operates automated Linux machines on premises and connects to AWS over Direct Connect. During initialization, each machine must mount an Amazon EFS file system to read configuration data. All NFS traffic must be encrypted in transit. The machines must use short-lived AWS credentials with least privilege, and administrators must be able to revoke one machine's AWS access independently without rotating credentials for every other machine. Which combination of steps best fulfills these stringent security requirements? Choose 2. More than one answer may be correct. Options. Option A. Use the open-source Linux NFS client directly to mount the file system, utilizing standard TLS tunneling. Option B. Use AWS IAM roles anywhere with a trusted certificate authority. Issue a unique X.509 certificate to each machine. Map the workload to a least privilege IAM role and configure the IAM roles anywhere credential helper as a credential_process, so each machine obtains temporary AWS credentials. Option C. Create a single IAM user with an access key and attach the Amazon Elastic File System Client read-write access policy. Distribute this single key pair to all on-premises machines to simplify rotation. Option D. Install Amazon EFS utils on each on-premises machine and mount the EFS file system with TLS and IAM authorization, using the temporary AWS credentials obtained for that machine. Option E. Create individual IAM users for every on-premises machine, generate long-lived access keys for each, and configure the AWS CLI on the machines using those keys. You should choose option B. Use AWS IAM roles anywhere with a trusted certificate authority. Issue a unique X.509 certificate to each machine. Map the workload to a least privilege IAM role and configure the IAM roles anywhere credential helper as a credential_process, so each machine obtains temporary AWS credentials. And option D. Install Amazon EFS utils on each on-premises machine and mount the EFS file system with TLS and IAM authorization, using the temporary AWS credentials obtained for that machine. Let's look at the reasoning. IAM roles anywhere is designed for workloads running outside AWS that authenticate with X.509 certificates and receive temporary IAM credentials. Giving each machine its own certificate supports independent revocation and least privilege role mapping. The EFS mount helper in Amazon EFS util supports TLS encryption and IAM authorization, allowing the mount to use those temporary AWS credentials. Now let's rule out the other options. A. A basic NFS client by itself does not provide the EFS IAM authorization workflow required by the scenario. Amazon EFS util supplies the EFS TLS/IAM mount integration. C. A shared long-lived IAM access key violates least privilege, increases credential exposure, and prevents independent revocation for one machine. D. Individual IAM users still rely on long-lived access keys and create unnecessary key rotation and secret distribution overhead compared with certificate-based temporary credentials. Exam tip. For non-AWS workloads that need temporary AWS credentials, IAM roles anywhere can authenticate X.509 identities. Use Amazon EFS utils for EFS mounts that require TLS and IAM authorization. Here comes question number 231. Here's the scenario. A security engineer creates a custom AWS config rule backed by an AWS Lambda function. The rule is designed to inspect Amazon Elastic Container Registry, Amazon ECR, repository policies, and identify any overly permissive statements. When a non-compliant policy is detected, AWS config leverages Amazon Event Bridge and Amazon SNS to alert the Security Operations Center. However, during testing, the AWS config dashboard shows the custom rule evaluation status as failed because the Lambda function is never executed. What is the most likely cause of this execution failure, and how should it be resolved? Review the options. Option A. The IAM execution role assumed by the Lambda function lacks the necessary ECR, get repository policy permissions. The execution role must be updated. Option B. The Lambda function's resource-based policy does not grant the configured Amazon AWS.com service principal permission to invoke the function. A Lambda add permission API call is required. Option C. The SNS topic policy is missing the required permissions to allow Amazon Event Bridge to publish messages to it. The SNS topic policy must be updated. Option D. The resource-based policies on the target ECR repositories are blocking AWS config from reading them. The ECR policies must be updated to allow AWS config access. In this case, choose option B. The Lambda function's resource-based policy does not grant the configured Amazon AWS.com service principal permission to invoke the function. A Lambda add permission API call is required. Here's why. When a custom AWS config rule is triggered, the AWS config service principal, configured at AmazonAWS.com, attempts to invoke the specified AWS Lambda function. If the Lambda function does not have a resource-based policy explicitly granting the config service principal the Lambda invoke function permission, the invocation will fail, resulting in a failed evaluation status on the AWS config dashboard. The other choices do not work because A, while the execution role needs ECR, get repository policy to read the policies, a failure here would result in the Lambda throwing an exception during execution, not failing to run entirely. The symptom described is the Lambda failing to execute when evaluated. C. SNS topic policies manage who can publish to the topic. While necessary for the final alert, an SNS failure would not cause the AWS config rule evaluation to show as failed. The evaluation would succeed, but the notification would drop. D. If the ECR repository policy denied access, the Lambda function would execute, but receive an access denied error when calling the ECR API. The scenario states the Lambda function fails to run at all. Whenever AWS config event bridge or S3 must synchronously invoke an AWS Lambda function, the Lambda function must possess a resource-based policy explicitly granting Lambda invoke function to that specific service principal. Question number 232. We're moving on to FSX ONTAP SnapMirror. Here's what is happening. A globally distributed enterprise uses a large on-premises NetApp ONTAP array that hosts read-only shared application binaries. The enterprise is expanding into 4 AWS regions and wants independent AWS-hosted copies that can be refreshed from the on-premises source on a defined replication schedule. The solution should use ONTAP native replication, retain ONTAP storage efficiency benefits such as deduplication and compression on the AWS targets, and keep the AWS copies available even when the direct connect link to the data center is unavailable. Which solution best meets these requirements? The choices are: Choice A, provision an Amazon S3 file gateway on-premises. Replicate the data to S3 buckets in all 4 regions, and use S3 cross-region replication, CRR, to keep them synchronized. Choice B, provision Amazon FSX for Windows file server instances in each of the 4 AWS regions. Configure an on-premises scheduled job to push updates using Robocopy. Choice C, provision Amazon Elastic File System, Amazon EFS, file systems in each of the 4 regions. Deploy an AWS Data Sync agent on-premises and configure scheduled tasks to synchronize the data. Choice D, provision Amazon FSX for NetApp ONTAP file systems in each of the 4 AWS regions. Configure native NetApp SnapMirror relationships between the on-premises array and the AWS file systems. The answer here is option D. Provision Amazon FSX for NetApp ONTAP file systems in each of the 4 AWS regions. Configure native NetApp SnapMirror relationships between the on-premises array and the AWS file systems. This works because Amazon FSX for NetApp ONTAP provides managed ONTAP in AWS and supports NetApp SnapMirror relationships from an on-premises ONTAP source. SnapMirror transfers snapshots to destination volumes and can be updated on a schedule, while FSX for ONTAP supports ONTAP storage efficiency features, such as deduplication and compression. The replicated data is hosted in AWS, so it remains available there when the on-premises network link is down. Here's why the alternatives are not suitable. A. S3 file gateway changes the storage model to S3 and does not provide ONTAP native SnapMirror replication or preserve the ONTAP storage efficiency model. B. FSX for Windows file server with Robocopy is a host-based file copy design, not ONTAP native replication, and it adds operational overhead. C. Data sync to EFS is a file-level transfer design and does not preserve the ONTAP native replication and storage efficiency behavior requested. A helpful shortcut is this. When the source is NetApp ONTAP and the requirement is ONTAP native replication to AWS, use FSX for NetApp ONTAP with SnapMirror. Next, question number 233. Scenario. A DevOps engineer has deployed a third-party application on an Amazon Elastic Kubernetes service, Amazon EKS, cluster. The application requires access to a database password stored securely in AWS Secrets Manager. The secret is encrypted using an AWS Key Management Service, AWS KMS, Customer Managed Key, CMK. The application pod relies on IAM roles for service accounts, IRSA, and successfully assumes a dedicated IAM role. The role's identity-based policy grants Secrets Manager, gets secret value. However, when the pod attempts to fetch the secret, it receives an access denied, HTTP 403 forbidden error. What is the root cause of this failure? Option A. The IAM role assumed by the pod through IRSA is not authorized for KMS. Decrypt on the customer managed KMS key. Grant KMS. Decrypt to the role for that key and ensure the KMS key policy permits the role's IAM authorization. Option B. The underlying IAM role assigned to the EKS worker node EC2 instances lacks the necessary permissions to retrieve secrets from Secrets Manager. Option C. The IAM role assumed by the Kubernetes service account lacks the required describe cluster permission necessary to execute API calls within the VPC. Option D. The KMS key policy attached to the customer managed key does not explicitly grant the EKS cluster's control plane IAM role the ability to use the key. The best choice is option A. The IAM role assumed by the pod through IRSA is not authorized for KMS. Decrypt on the customer managed KMS key. Grant KMS. Decrypt to the role for that key and ensure the KMS key policy permits the role's IAM authorization. The main reason is get secret value for a secret encrypted with a customer managed KMS key also requires KMS. Decrypt on that key. Secrets Manager performs the KMS operation on behalf of the calling principal. The permission can be established through IAM and the key policy according to the key policy design. The decisive defect is that the IRSA role lacks effective KMS decrypt authorization. The remaining options can be eliminated because B. With IRSA, the application pod uses its service account role for AWS API calls instead of relying on the EC2 node role. C. X. Describe cluster is not required for the application to retrieve a secret from Secrets Manager. D. The EKS control plane role is not the principal making the application's get secret value request and does not need to decrypt this secret on the pod's behalf. Keep this point in mind for the exam. For Secrets Manager secrets encrypted with a customer-managed KMS key, the calling principal needs both Secrets Manager, get secret value, and effective KMS, decrypt authorization for the key. Question number 234. Let's go. This is a harder question, so check every requirement carefully. A heavily regulated healthcare company manages its workloads in an AWS organization's multi-account structure. Application teams deploy to dedicated workload accounts, while common infrastructure resides in a shared services account. Compliance dictates that every container image must be strictly scanned for vulnerabilities before it is permitted in a production environment. Only images that pass the scan with zero critical vulnerabilities can be exposed to downstream deployment pipelines. To guarantee isolation, untested images and approved images must reside in entirely separate repositories. Which combination of actions establishes this centralized scanning workflow with the least administrative overhead? Choose 2. Identify all valid responses. Choices. Option A. Create Amazon Elastic Container Registry, Amazon ECR, pre-scan and post-scan repositories centrally in the shared services account. Grant workload accounts write access to the pre-scan repositories and read access to the post-scan repositories via resource-based policies. Option B. Create pre-scan Amazon ECR repositories in every individual workload account. Create the post-scan repositories centrally in the shared services account. Grant workload accounts read access to the post-scan repositories via resource-based policies. Option C. Create an event bridge rule for Amazon Inspector/ECR scan completion events. Invoke a Lambda function to evaluate the scan result, and only for compliant images, start one centralized code build promotion job that pulls the image from the pre-scan repository, retags it, and pushes it to the post-scan repository. Option D. Build a dedicated AWS code pipeline for every pre-scan repository. Configure an AWS code build stage that executes a script to parse the scan results and uses the Docker CLI to push compliant images to the post-scan repositories. Option E. Enable native cross-account EC or image replication to automatically mirror all pushed images from the pre-scan repositories to the post-scan repositories regardless of scan status. The answers that work here are Option A. Create Amazon Elastic Container Registry, Amazon ECR, pre-scan and post-scan repositories centrally in the shared services account. Grant workload accounts write access to the pre-scan repositories and read access to the post-scan repositories via resource-based policies. And Option C. Create an event bridge rule for Amazon Inspector/EC or scan completion events. Invoke a Lambda function to evaluate the scan result, and only for compliant images, start one centralized code build promotion job that pulls the image from the pre-scan repository, retags it, and pushes it to the post-scan repository. This is the best choice because centralizing both pre-scan and approved repositories in the shared services account minimizes the number of repositories and cross-account policies that the security team must manage. Enhanced EC or scanning through Amazon Inspector emits event bridge events. A lightweight Lambda gate can evaluate the findings and start a single centralized code build promotion job only for compliant images, preserving the required physical separation between untested and approved repositories. Let's quickly check the incorrect choices. B. Creating pre-scan repositories in every workload account multiplies repository policies, scan configuration, event rules, and operations across the organization. D. A dedicated code pipeline and code build project for every repository creates substantially more administration than one centralized event-driven promotion workflow. E. EC or replication is not conditional on vulnerability findings. It would replicate unapproved images and violate the separation requirement. Here's a useful exam tip. For gated container promotion, keep untrusted and approved EC or repositories separate and use scan findings as the event-driven gate before a controlled image copy/push. Next, question number 235. Scenario. A logistics company operates a serverless application utilizing Amazon EventBridge to route order processing events between loosely coupled microservices. Recently, developers reported that a specific EventBridge rule is failing to deliver events to its downstream target during load testing. The testing environment is strictly locked down. The DevOps team is expressly forbidden from modifying or redeploying the application source code. The developers urgently need visibility into the unmatched events, a way to troubleshoot the delivery failures, and a mechanism to ensure no failed events are permanently lost. Which steps should the DevOps team take to fulfill these requirements without altering application code? Choose 3. Choose every option that satisfies the requirement. Options. Option A. Deploy AWS Device Farm and provision a standard testing environment to synthetically simulate the application's event generation patterns. Option B. Add an Amazon SQS standard queue to the problematic event bridge rule and configure it as a dead letter queue, DLQ, to capture delivery failures. Option C. Enable AWS X-ray tracing by instructing developers to instrument the application codebase with the X-ray SDK to trace the event lifecycle. Option D. Enable Amazon EventBridge event bus logging at trace level to a CloudWatch logs log group, including execution data, so the team can inspect event receipt, rule matching, or NO_standard_match records, target invocation attempts, and delivery failures. E. Add an Amazon SQS FIFO queue to the problematic event bridge rule and configure it as a dead letter queue, DLQ, to capture delivery failures in strict order. F. Monitor the event bridge rule and target with CloudWatch metrics such as failed invocations, invocation attempts, and invocations sent to DLQ, and create alarms or a dashboard to surface delivery failures. The correct answers are Option B. Add an Amazon SQS standard queue to the problematic event bridge rule and configure it as a dead letter queue, DLQ, to capture delivery failures. Option D. Enable Amazon EventBridge event bus logging at trace level to a CloudWatch logs log group, including execution data, so the team can inspect event receipt, rule matching, or NO_standard_matched records, target invocation attempts, and delivery failures. And Option F. Monitor the event bridge rule and target with CloudWatch metrics, such as failed invocations, invocation attempts, and invocations sent to DLQ, and create alarms or a dashboard to surface delivery failures. An event bridge target DLQ must be an SQS standard queue and preserves events that event bridge cannot deliver after retries. EventBridge event bus logging can now send detailed processing records to CloudWatch logs. Trace logging can expose event receipt, rule matches, NO_standard_matched, invocation attempts, retries, and DLQ activity without application code changes. CloudWatch EventBridge metrics provide a separate operational signal for failed invocations and DLQ delivery, making alarms and dashboards useful for troubleshooting. AWS Device Farm is for testing mobile and web applications. It is not an EventBridge event delivery diagnostic mechanism. C. Adding X-ray instrumentation requires application code changes and redeployment, which the scenario explicitly prohibits. E. EventBridge target dead letter queues support Amazon SQS standard queues, not FIFO queues. The main takeaway is for EventBridge delivery troubleshooting without code changes, combine event bus trace logs, CloudWatch delivery metrics, and an SQS standard target DLQ. Question number 236. Let's go. A DevOps engineer manages an AWS CloudFormation template that provisions an Amazon S3 bucket used for hosting static assets. The template also includes an AWS Lambda-backed custom resource that dynamically downloads configuration files and writes them into the S3 bucket during stack creation. The team needs to tear down the environment, but when the engineer initiates a stack deletion, CloudFormation successfully deletes the custom resource, but fails to delete the S3 bucket, ultimately causing the stack deletion to fail and roll back. What is the root cause of this failure, and how should it be resolved for future deployments? Option A. CloudFormation cannot delete an S3 bucket if it contains objects. The Lambda function backing the custom resource must be updated to recursively delete all objects in the bucket when it receives a delete request type. Option B. CloudFormation requires an explicit deletion instruction. The engineer must add a deletion policy property with a value of empty directly to the S3 bucket resource definition in the template. Option C. The S3 bucket has an active website configuration preventing its deletion. The engineer must remove the website configuration property from the S3 bucket resource in the template before deleting. Option D. The custom resource is missing a lifecycle policy. The engineer must add a deletion policy property with a value of remove on deletion to the custom resource definition in the template. Go with option A. CloudFormation cannot delete an S3 bucket if it contains objects. The Lambda function backing the custom resource must be updated to recursively delete all objects in the bucket when it receives a delete request type. Let's look at the reasoning. By design, AWS CloudFormation will fail to delete an Amazon S3 bucket if it is not completely empty. Because the custom resource dynamically placed objects into the bucket after it was provisioned, CloudFormation's native deletion fails. The appropriate operational best practice is to design the custom resource Lambda function to handle the CloudFormation delete event, request type, delete, by programmatically emptying the bucket before signaling success back to CloudFormation. Now let's rule out the other options. B. AWS CloudFormation does not have an empty value for the deletion policy attribute. The valid values are delete, retain, and snapshot. C. While an S3 bucket can have a website configuration, this metadata does not prevent CloudFormation from deleting the bucket. The presence of physical objects inside the bucket is what blocks deletion. D. A deletion policy on the custom resource itself dictates whether the logical resource is retained in the stack metadata. It does not force the Lambda function to take action against the S3 objects. Exam tip. When CloudFormation fails to delete an S3 bucket because it contains dynamically generated objects, the standard solution is to implement an AWS Lambda-backed custom resource that empties the bucket during the stack deletion lifecycle. Question number 237. Scenario. A corporate backend service exposes internal API is via Amazon API Gateway within an AWS organization's member account. To enhance security, the networking team restricted the API so they can only be accessed internally through an interface VPC endpoint. The security team updated the VPC endpoint policy with the following condition, for any value, string like, AWS, principal org paths, oexample/rroot/ou internal. The API Gateway Resource Policy was also updated to explicitly deny any invocations bypassing the VPC endpoint. However, testing reveals that internal client applications are now receiving an access denied error. User, anonymous, is not authorized. Which combination of actions will authenticate the clients and resolve this error? Choose 2. Select all answers that apply. Choices. Option A. Update the API gateway configuration by setting the authorization method of all relevant API methods to AWS_IAM. Option B. Implement an AWS Lambda authorizer configured to accept token-based authentication and pass a bearer token containing the caller's organizational identity. Option C. Integrate Amazon Cognito user pools with the API gateway as the primary authorizer to validate the internal corporate directory credentials. Option D. Update the client applications to cryptographically sign their HTTP requests using signature version 4, SigV4, with valid AWS credentials. Option E. Implement a request parameter-based AWS Lambda authorizer to extract and validate the caller's identity from a combination of headers and query strings. The required selections are Option A. Update the API gateway configuration by setting the authorization method of all relevant API methods to AWS_IAM, and Option D. Update the client applications to cryptographically sign their HTTP requests using signature version 4, SigV4, with valid AWS credentials. Here's why. The VPC endpoint policy utilizes the AWS principal org paths condition key. This key relies on AWS IAM to cryptographically verify the caller's identity and determine their location within the AWS organization's hierarchy. Anonymous HTTP requests contain no IAM identity context, causing the policy to fail. To resolve this, the API gateway methods must be configured to demand AWS_IAM authorization, and the client applications must use signature version 4, SigV4, to sign their requests with valid AWS IAM credentials, proving their identity to the endpoint. The other choices do not work because B. A custom Lambda authorizer validates custom tokens, like JWTs, and returns a generic IAM policy, but it does not natively provide the AWS principal org paths context to the underlying VPC endpoint policy evaluation engine. C. Amazon Cognito user pools authorize external or federated users but do not inherently translate into native IAM principles that satisfy the AWS principal org paths condition on the VPC endpoint without complex identity pool exchanges. E. A request parameter-based Lambda authorizer is useful for custom logic, but like a token authorizer, it bypasses the native AWS IAM signature verification required by the VPC endpoint to evaluate organization paths. Whenever an AWS resource policy or VPC endpoint policy relies on IAM conditions like AWS principal org paths or AWS principal account, the client must sign the request using SigV4, and the service must be configured for AWS_IAM authorization. Question number 238. Let's go. Scenario. A startup runs its flagship application on Amazon Elastic Kubernetes Service, Amazon EKS. Currently, developers manually build Docker images on their local machines and push them to the cluster, which has become unscalable as the team grows. A DevOps engineer needs to automate the container build process whenever code is pushed. Furthermore, security policies require an immediate automated Amazon SNS notification if a Docker image is built that contains high or critical severity vulnerabilities in its operating system packages. Which combination of steps creates the most robust and native automated solution? Choose 2. Select all answers that apply. Options. Option A. Store the application code in AWS Code Commit. Create an Amazon Event Bridge rule that detects repository branch updates and triggers an AWS Code pipeline that invokes an AWS Code Build project to build the image. Option B. Store the application code in AWS Code Commit. Configure an Amazon S3 event notification on the underlying repository bucket to trigger an AWS Code pipeline that invokes an AWS Code Build project. Option C. Configure the AWS Code Build project to push the built Docker image to an Amazon Elastic Container Registry, Amazon ECR, repository with enhanced scanning enabled. Create an Amazon Event Bridge rule that monitors inspector scan events and triggers the SNS topic if critical or high findings exist. Option D. Configure the AWS Code Build project to execute a local Docker file scan and only push the image to an Amazon Elastic Container Registry, Amazon ECR, repository if the local scan passes. Configure the SNS topic to alert on code build failures. E. Configure the AWS code build project to push to an Amazon Elastic Container Registry, Amazon ECR, repository with basic scanning enabled. Create an Amazon Event Bridge rule that monitors Amazon Guard Duty events for image vulnerabilities and triggers the S&S topic. The correct answers are option A. Store the application code in AWS code commit. Create an Amazon Event Bridge rule that detects repository branch updates and triggers an AWS code pipeline that invokes an AWS code build project to build the image, and option C. Configure the AWS code build project to push the built Docker image to an Amazon Elastic Container Registry, Amazon ECR, repository with enhanced scanning enabled. Create an Amazon Event Bridge rule that monitors inspector scan events and triggers the S&S topic if critical or high findings exist. This works because to automate the build process natively, AWS code commit state changes, like a push to a branch, are easily captured by Amazon Event Bridge, which then triggers an AWS code pipeline orchestration that runs code build. To automate security scanning, pushing the image to Amazon ECR with enhanced scanning delegates the vulnerability analysis to Amazon Inspector. Inspector natively emits structured Inspector 2 scan events to Event Bridge, allowing a simple rule to filter for high or critical findings and trigger the S&S notification with no custom scripting required. Here's why the alternatives are not suitable. B. AWS Code Commit is a managed Git service. It does not utilize Amazon S3 event notifications for branch updates. You must use Event Bridge to capture code commit repository state changes. D. Executing a local Docker file scan inside code build requires custom scripts, management of third-party scanning tools, and manual parsing of results, which introduces heavy operational overhead compared to native ECR enhanced scanning. E. ECR basic scanning utilizes the open-source Claire engine and emits ECR image scan events, not Amazon Guard Duty events. Guard Duty does not perform static container image package scanning in ECR. A helpful shortcut is this. For native AWS container security automation, push images to Amazon ECR with enhanced scanning enabled. This integrates with Amazon Inspector, which emits actionable scan findings directly to Amazon Event Bridge. Question number 239. The focus now shifts to image builder distribution. A global SaaS provider standardizes its microservices on a common golden container base image. To address compliance requirements, a DevOps engineer must implement an automated pipeline to build a new hardened version of this base image every week. Once built, this golden image must be automatically published to Amazon Elastic Container Registry, Amazon ECR, repositories in the US, East, 1, EU, West, 1, and AP, Northeast, 1 regions so regional development teams can consume it locally. Which solution meets these requirements with the most native automation? Choices. Option A. Configure an EC2 image builder pipeline utilizing a container recipe to build the golden image. Define an image builder distribution configuration targeting the ECR repositories in all 3 required regions. Schedule the pipeline to run weekly. Option B. Configure an EC2 image builder pipeline utilizing a container recipe to build the golden image and push it to a primary ECR repository in US, East, 1. Configure ECR cross-region replication to sync the image sequentially to the other 2 regions. Option C. Configure an AWS code pipeline that triggers an AWS code build project to build the image weekly. Add an AWS code deploy stage to handle the concurrent publishing of the image to the ECR repositories in all 3 regions. Option D. Configure an AWS code pipeline that triggers an AWS code build project weekly. Add a custom post-build script using the AWS CLI to manually tag and push the resulting image to the ECR repositories in all 3 regions. The right response is option A. Configure an EC2 image builder pipeline utilizing a container recipe to build the golden image. Define an image builder distribution configuration targeting the ECR repositories in all 3 required regions. Schedule the pipeline to run weekly. The main reason is EC2 Image Builder provides a fully managed, native pipeline specifically designed for automating the creation, hardening, and distribution of both Amazon EC2 AMIs and Docker container images. By defining an image builder distribution configuration, The service natively handles pushing the resulting image to the specified Amazon EC/R repositories across multiple AWS regions, fulfilling all requirements with a single managed service and zero custom scripting. The remaining options can be eliminated because while EC/R cross-region replication is a valid feature, EC2 Image Builder already has native multi-region distribution capabilities built in. Relying on Image Builder distribution provides a single pane of glass for the pipeline success rather than relying on decoupled replication rules. AWS Code Deploy is an application deployment service designed to deploy software to compute platforms, EC2, ECS, Lambda. It is not designed to push or replicate container images between EC/R repositories. Utilizing code pipeline and code build with custom AWS CLI scripts introduces unnecessary operational overhead, custom code maintenance, and error handling for multi-region pushes, which EC2 Image Builder handles natively out of the box. Keep this point in mind for the exam. For the automated creation, hardening, and multi-region distribution of golden machine images, AMIs, and container images, EC2 Image Builder is the most operationally efficient AWS native tool. You have completed Set 13 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.